The first reason for that, this is some of the recent forecasts. So there are several published works in the literature from the last couple of years that are indicating that there would be a reasonable possibility of strong lensing detections once the current gravitational wave detectors reach design sensitivity or A+ sensitivity, meaning in the next couple of years. And so this is one of the reasons why there's been a push to develop the methodologies to detect gravitational wave lensing. And the second reason, which maybe is the even more important reason, is that if we were to realize gravitational wave lensing in practice, then this would be a new way to detect gravitational lensing, and it would also constitute a new source of gravitational waves. And so these are some of the reasons why some of the reasons that has been motivating the recent studies into gravitational wave lensing. Okay, so hopefully I've given a little bit of motivation why we think gravitational wave lensing is a worthwhile topic to look into, and we can move on to some of the more detailed detection methodologies. So how do we actually detect gravitational wave lensing? So this depends on the lensing signature. So here I show three different gravitational wave lensing signatures. There is firstly lensing magnification. So what happens when a gravitational wave is being lensed is that the amplification or the amplitude of the gravitational wave grows. So that's something that we might try to look for in the gravitational wave data. Another possibility is multiple images, but instead of observing the multiple images as images by themselves, what we're observing is repeated events. So we're trying to look for events that look nearly identical and come from the same sky localization. The third possibility is wave optics distortion. So what we're asking here is the question, could it be that some of the gravitational waves that we've seen, could it be that they've gone through a field of microlenses or millilenses, in which case the waveform would be modified like this, so that they have beating patterns in the gravitational wave waveform. So these are the signatures that we're looking for. And if we go into a little bit more details into the magnification, so what exactly happens when there is lensing magnification? How do we detect it? So it turns out that this is one of the more tricky signatures of gravitational lensing or gravitational waves. And for a long time, it was thought that it is not possible for us to purely detect lensing magnification. And the reason is simply because when we have a highly magnified event, we can't really tell if it is genuinely a magnified event or if it is a binary black hole that is closer to us. So there is a degeneracy between the luminosity distance and the magnification measurement. But then a couple of years back, together with a PhD student from NICEF, we worked on trying to tackle this problem with binary neutron stars. So it turns out that binary neutron stars allow us to measure the tidal effects from binary neutron stars, and that allows us to understand the inner structure of neutron stars, which allows you to measure both the mass of the neutron star and also to some degree what the distance of the neutron star is. And that measurement is unaffected by lensing. And this allows us to detect binary neutron stars even with a single magnified signal. And so what we wanted to do is we wanted to analyze this 190425 GW190425 event, which was a high mass binary neutron star detection, and we ruled it out as a lensed event. And so to summarize it, what magnification does to the waveform is that it changes its amplitude. It's quite tricky to detect it with binary black holes, but it is possible to do it with binary neutron stars. All right, so the second signature is strong lensing. So how do we detect gravitational wave strong lensing? So what you can see here on the top left is a illustrative graph of a multiple imaged waveform. So there are two gravitational wave events, and they have exactly identical frequency evolution. So that is one of the predictions of strong lensing for gravitational waves. And we can essentially try to identify strong lensing by looking for two gravitational wave events that have the same exact identical frequency evolution. So suppose that we have a catalog of gravitational wave events, then to look for event pairs and asking the question, is it possible that these event pairs are strongly lensed? What we do is we try to contrast, are these gravitational wave waveforms identical? and do they come from the same sky location? If they are identical and they come from the same sky location, then they constitute a strong lensing candidate. But in order for us to verify that it is truly a strongly lensed gravitational wave, we also have to rule out the possibility that there are actually two gravitational wave events that happen to have the same frequency evolution, happen to have the same sky location, just by pure coincidence. And we do this through Bayesian analysis. So we published some last year a software for doing this strong lensing analysis for both detecting gravitational wave events that are strongly lensed, but also combine any detections in a joint analysis to look at the image properties, so magnifications and time delays and Morse phases of strongly lensed gravitational wave events. All right, so essentially for strong lensing, what we look for is identical signals or event repeaters that come from the same sky location. So the third possibility is asking the question, is it possible that maybe one of the gravitational wave events that we've seen, maybe they propagated through a field of microlenses like the one that you see here? So what would be the implications here? So what would happen is that these different micro images that you can see here, there are, I think, 7 of them or 8 of them, they would recombine at the gravitational wave detector and superpose and form these sort of beating patterns that you can see at the top left. And so when someone asks, well, how do you detect microlensing? What we're really trying to do is we're trying to locate these sort of beating patterns that could exist in the gravitational wave data. So we do templated searches for gravitational waves. All right, so these are sort of the 3 different signatures and how you can look for them. But then in 2019, we did a first search for gravitational wave lensing with several collaborators. And what we tried to do is look for signatures magnification. So we basically tried to figure out, could maybe some of these high mass gravitational wave events that we've seen, some high mass binary black holes, could they maybe be actually from a population of lower mass binaries, but were heavily magnified. We tried to look for repeated events, so multiple images, where you can see the results being summarized on the right, where all of the detections were below 2 sigma. So we essentially here looked at all of the permutations of different event pairs in the gravitational wave detectors. We tried to test, are these, do they have the same frequency evolution, and do they come from the same sky location? And then we tried to contrast this with the astrophysical background, and all of them were below 2 sigma level. And so we couldn't make any confident detections of strong lensing. And then finally, we also looked for micro lensing, which you can see at the bottom left, where we did a templated search using a simple point mass lens model. And we analyzed all of the gravitational wave events in the GWTC1, so observing runs 1 and 2. And essentially, we concluded there is no signature of microlensing. Or at least there is no compelling evidence that any of these would be microlensed. So since 2019, there's been a lot of push for these gravitational wave searches also at the collaboration level. So last year, we put out a paper with the LVK collaboration to look into signatures of gravitational wave lensing in the GWTC2, so the latest gravitational wave, observing runs 1, 2, and 3 for gravitational lensing signatures. And we did much of the same analysis. So we looked for signatures of microlensing, for magnification, and also multiple images. Ultimately, we concluded that there is no compelling evidence as of yet of signatures of gravitational wave lensing in the data. But the important thing I think to maybe mention here is that this also shows that some of the search methodologies that we have, they're mature enough that they can be applied for real data. And I think this is also a very good step in the direction of implementing gravitational wave searches at a collaboration level. All right, so these are some of the search results, and then hopefully in the future, as the gravitational wave detectors become more sensitive, we actually do get detections. But one of the questions that is also important to keep in mind is that, what do we actually do once we see a gravitationally lensed gravitational wave? What are some of the interesting science cases? So one of the things that we've been looking into recently is this idea that if we have a strongly lensed gravitational wave event from a binary black hole, then we can try to locate the host lens system. So we can try to figure out which galaxy the binary black hole came from. And the idea is quite simple. So the idea is that if you have a binary black hole that exists in a galaxy and it is strongly lensed, then the light from the galaxy should also be strongly lensed, which means that if you pinpoint telescopes in the direction where the gravitational wave came from, then you should be able to see something like the strongly lensed galaxy over here. So that is the idea. And the one of the difficulties, of course, is that there would be several different strong lensing galaxies in the direction of the gravitational wave. But if you combine gravitational wave measurements with electromagnetic lensing reconstructions, then you can rule out some of the false positives and hopefully narrow down the search to 1 or 2 lens host galaxies. And so the reason that this is interesting is, not so much just because we can localize binary black holes, but the other reason is that we will, once we've actually done it, so supposing that this is possible, that we've located a binary black hole to its host galaxy and host lens system, then we can analyze the lens system both in the gravitational wave band and also in the electromagnetic band. And so this is very attractive from the perspective of joint analysis. So because electromagnetic information gives us one set of information, gravitational waves sort of give us another set of information, and there are some interesting science cases that may be possible for this reason. So one of the things that we investigated with some collaborators from Groningen is the localization of binary black holes using this methodology. So one of the things that you may be able to do with a combined measurement like this is to locate binary black holes down to sub-arc second precision. So figuring out where the binary black holes came from within the galaxy. And this would be the most precise way to localize binary black holes. The other possibility is Hubble constant measurements. So this was work with some of the folks from Portsmouth to look into how you can use this sort of measurement to measure the Hubble constant from time delay distances and also from luminosity distances. And then we have another work with a PhD student from Utrecht University to look into how you can use the same measurement also to do tests of modified gravity. And so what you can see here is an example of how you can use the same measurement to probe extra dimensions, scalar tensor theories, and theories with varying Planck mass. And the main reason that this is attractive is because we will be able to get a localized event from high redshift. And if the event is from high redshift, then the gravitational wave will have some time to accumulate any propagation effects that would come from modified gravity that would sort of accumulate on the waveform and allow you to do better modified gravity tests. There was also a really nice paper from Fink et al. From last year, looking into this with the scalar tensor theories or this psi parameterization. All right, so these are the sort of 3 applications that we've been looking into. I think that there are also a lot of interesting, other interesting science cases. I think Graham Smith will be talking a little bit more about the multimessenger aspects of lens kilonovae, which I think also has interesting science applications. But what I'd like to say is that if we were to sort of detect gravitational wave lensing and analyze it, I think there's a lot of interesting science that could be done. All right, so let me say a few words about the future outlook and challenges, and maybe focusing on some of the things that I'm hoping to get from this conference. Is that one of the sort of big challenges that we've had is that our lensing analysis and detection methodologies rely quite heavily on lens modeling, so lens population modeling, and also binary black hole population modeling. But right now, the community doing gravitational wave lensing is very much, at least from the LVK side, is very much from the gravitational wave community, which means that we're very much behind, I think, in progress in lens modeling and also lens population modeling. And so there's a lot of work to be done on that side. And the other thing that where I think that there is some possible synergies is with looking into these sort of combined measurements where you can try to look for electromagnetic lens modeling and try to combine that with gravitational waves. So there is some promise in that area, and I think that in the future there will be more work in that direction. And so my hidden agenda here is to learn as much as I can about electromagnetic lensing and try to take home some of the things to the gravitational wave community. So with that, I would like to thank you very much for your attention, and I'll welcome any questions.
Thank you so much, Otto. Any questions?
So you had mentioned testing modified gravity models with this. What does the EM information add? Can you, for example, learn more about whether it's dynamical Chern-Simons or EDGB if you have both GW and EM signals? Because I thought with just the GW signal, all you'll see is a frequency shift, yes, or a phase shift.
Yeah. So that's a very good question. So the two components that go into these modified gravity analysis, the ones that we were looking into, they were specifically looking at modified gravity theories where the gravitational wave propagation is modified. So for example, if you have extra dimensions, some of the gravitational wave energy could be leaking into other dimensions that we couldn't observe. And if that is true, then one of the sort of effects that you expect if you go to higher redshift is that any propagation effects will accumulate for a longer time than if you had a lower redshift event. And so far, most of these analyses have been done with lens kilonovae or normal kilonovae or BNSs, which typically come from lower redshift. And so essentially, the assumption here is that you get a redshift measurement of the host galaxy, and you can relate that to the luminosity distance. And it's the luminosity distance that gets modified in these propagation theories. But there are also many other modified gravity theories. I think there's some interesting work also into modified polarization, where you could use gravitational wave lensing to effectively increase your number of detectors, which allows you to probe more degrees of freedom of different polarization theories.
Other questions? I think I saw one from over here.
Thanks. Yeah, strongly lensed gravitational wave. Wow, that is really cool. Thank you for this talk. That was very cool. My question related to that is, do you have a sense for how detectable, how resolved in time the differences between two lens gravitational wave events are going to be? Like, my question is basically, do we expect the two signals that you show to be well separated, or are they going to be blended? And this, I guess, depends on the population of these gravitational wave events and where they happen in relation to the lens.
Yeah, so just to make sure I'm understanding the question correctly, so it's that the question is whether or not the waveforms would be sort of overlapping or whether or not they would be well separated. Yeah, it depends a little bit on the lens that produces them. So for example, if we have a galaxy lensing setup, then the lensing time delays, if they're, let's say, order of hours to days to months to maybe years even, then the gravitational wave signal length is about 300 milliseconds for CBC signals, which means that they would be well separated. But if we're looking at millilensing, where the lens mass is much smaller and the time delay is therefore smaller, or microlensing, then you would have overlapping signals and you would have these beating patterns that you can try to look for. One of the differences that I could maybe mention very quickly about microlensing is that in terms of gravitational waves, there are also wave optic suppression effects that actually suppress microlensing, which means that microlensing happens quite differently for gravitational waves than it does for light lensing. But it's a very good question, and yeah, it depends. Basically, if we're in the limit of millilensing, or we're going to, let's say, lens masses smaller than 10 to the 5 solar masses, then you have overlapping signals. If the lens mass is bigger, then you have well separated signals, and you're trying to look for event repeaters.
What do you mean? The tools for the gravitational wave event are going to happen to the gravitational wave?
Yeah. It's a very good question.
Okay, we have time for maybe one more quick question. Patrick, anyone on the Zoom? No, if not, in person.
Simon Beer, for those on Zoom. Very nice talk, Otto. I was wondering, given like the next generation gravitational wave detectors, so Cosmic Explorer, Einstein telescope, they're very sensitive and hence even more biased towards strong lenses in terms of the stream amplitude. One is more biased towards strong lensing than even in optical. Can this potentially be, say, an issue or a need to really know what is lensed on a population level to do even the science that I aim for? So, for example, detecting the earliest gravitational waves.
So are you asking about whether or not it would be the fact that we get a number of events in, let's say, Einstein telescope or Cosmic Explorer, whether or not that would be an issue for the strong lensing detection? Or
the opposite, that whatever sample studies you do with these telescopes, whether you inherently must account for strong lensing selection effects.
Oh, yeah. That's a good question. So basically, whether or not the lensing effect could bias some of the measurements that we actually see in Einstein telescope and Cosmic Explorer.
Correct.
So I know that there have been studies for that with LISA. So we have one student together with actually Martin Henry and some of the folks from Glasgow to look into de-biasing or de-lensing the LISA measurements. I think it's going to be a bigger problem for LISA than it does for Einstein telescope. Although there's been also discussion about Einstein telescope, I think in the context of weak lensing. But yes, I think the higher the redshifts are, and the further we can actually probe gravitational wave events, the more important it becomes to also de-bias some of the results. It's probably not going to be a problem in LIGO Virgo because we get such a small number of events, but yeah, in Einstein telescope and in LISA, it becomes increasingly more important to consider lensing as a source, even in the just vanilla regular analysis. It's a very good question.
All right, we got to keep it moving, but let's give another round of applause for Otto. Next, I believe we have